Today I want to take a look at the imaginary unit. We're going to talk about several different things, and this comes from section 1-5 in your advanced algebra textbook. To this point we've had a few issues when we ran into taking square roots. If we had a problem such as x squared plus 1 is equal to 0, I've shown you how to solve this using the extraction method, which is essentially just taking the square root. So we'll isolate the variable. X squared is equal to -1. Therefore, as we learned the other day, x is equal to plus or minus the square root of -1. And up until this point, we've had some serious issues, because if you try to type that in your calculator, it obviously gave you an error, because there is no real number that if we square it, neither positive or negative, will it give us a negative number. Alright. Now, to get around this, what we have is we have something called the imaginary unit, and it's just a definition. And we define that the square root of -1 is actually going to be the lowercase I, which stands for the imaginary unit. Make sure when you're writing the imaginary I, the letter itself, that you're putting a tail on it and that it is lowercase. That way we don't mix it up with it being a 1 or any other variable or number. Now this is part of the definition. So if I is equal to -1, we also need to say, well, if I have I times I, which would be I squared, we need to define that as being equal to -1. These two ideas right here are the new concepts in section 1-5 that are going to allow us to solve solve quadratic equations that have non-real roots. Now let's investigate a couple powers of I. You're going to encounter in your homework, there's going to be several questions that say, well, we know that if I to the first is the square root of -1, they're going to ask you, well, what would I squared be? Well, we know that. I just said that it's defined as -1. But then if we continue to expand that and we say, well, what is I to the third? Well, how can we analyze it? We're going to say, well, I to the third algebraically is really I squared times I to the first. Well, -1 times the square root of -1 is really just the negative square root of -1. Another way to interpret that would be negative I, a negative I. So this would be really the same thing as negative I if you were to simplify it all the way in terms of I, and that's really what we're trying to go after here. Now if we do the same thing continuing on and I ask you, what is I to the fourth? Hopefully you'd tell me, well, that's really I squared times I squared. And if every I squared is -1, what we're really looking at is -1 times -1, which is really 1. Now using this concept, what we're going to see is that if I had I to the fifth, again, I could write that as pieces of this. It's pretty convenient to use I to the fourth times I to the first. Well, if I to the fourth is equal to 1, doesn't that mean that this is 1 times I to the first, which is just I to the first? Now what happens here is this whole idea is cyclic. It cycles around every 4 power. So essentially what we can say is that I to the fifth is really just the same thing as I to the first. And if I had another I to the sixth, well, since that's the second term, that's really just the same as I squared. And it continues on. In your homework, you're going to encounter questions such that say, well, if you had I to the 41st power, what would it simplify to? Well, we know that that's equivalent to I to the 40th times I to the first. And any multiple of 4, which is 40, is really just going to be I to the fourth times I to the fourth times I to the fourth times I to the fourth 10 times. Or 1 times 1 times 1 10 times, and they cancel out. They're really just the number 1. So at the end of the whole process, we're really just left with I. Now, let's take a look at something that we're going to use that imaginary unit in terms of simplifying it into the imaginary unit. So if we're provided something like the square root of -12, we know that that cannot be done in the real number system. Our first step is to extract the -1, the square root of -1, which is the imaginary unit. So I know that I can write this really as the square root of 12 times the square root of negative 1. Once I've done that, I know that this square root of negative 1 is really just I, the imaginary unit. So that means that this is really the square root of 12 times I. Now, we know from problems earlier in the year that this square root of 12 can really reduce, and we know that this is really root 4 times root 3I, which simplifies to 2 root 3I. We need to make sure that the I does not fall underneath of the square root of 3. A lot of times in class you'll see me put this coefficient, you can think of it as, or in parentheses, and that is our final answer. Now, let's tackle another one that is very similar, but I want to show you how I would approach it as if, you know, I wasn't demonstrating, I was just doing it in my homework, which is pretty much what I would expect you to do. So again, let's look at a second example here. And on this second example, let's just take the square root of negative 18. Now, as a student, the first thing I would do, since we've mastered simplifying radicals, I know that the largest perfect square is 9. Okay, so I wouldn't mess around with all this extra stuff like I did over here. I would simply say, well, this is root 9 times root 2I. That gets rid of the negative 1. And so, you know, the only step that I got left is 3 root 2I. And I'm going to circle the answer. So those problems, they move that quickly. Now, the next thing I'm going to throw at you is something called the complex number. And the complex number uses the imaginary unit and the real unit. Believe it or not, you've been using this for a long time. We've just kind of canceled out some of them. So the second part that I'd like to take a look at is called the complex number. Which we like to think of as the standard form of a complex number. Now, the complex number is always a plus bi. This is the standard form for it. Alright, let's underline this so we know that this is our heading. This is considered the real part. These are the numbers we've always used. It can be any number. It can be rational, irrational, does not make a difference. And then we take this part right here, and this is called the the imaginary part. And together, both of these things form what we call a complex number. A complex number has both a real part and an imaginary part. Now, two things to note about these. The numbers a and b, these variables represent the coefficients. They are both real numbers, meaning they can be fractions and positive and negative integers, and believe it or not, they can be 0. And that is what you have seen before. So back up to this point, I may say, give me a number. And maybe you gave me the number 21. This is the real part of it. We could think of this as being 21 plus 0i. Because the imaginary part just doesn't exist, we truncate it and a lot of times leave it off. Consequently, it can go in the other direction. We've just been dealing with imaginary numbers, such as this one from the previous example up here. I could have written this as 2 root 3i, but that is only the imaginary part. The real part is 0. So to write them as a complex number, we could say, well, this is the real part, this is the imaginary part, where a is 21 and b is 0. In our second example, the real part is 0 and the imaginary part has a b that is 2 root 3, which is a real number, but it's the coefficient on the imaginary. Now the next thing we're going to look at involving complex numbers is how would we multiply these things and how would we combine like terms. And I'm going to jump through all the basics and we're going to look at expansion of two binomials, all right, two complex numbers. Now the perk of all this is a lot of the stuff that you have learned with basic algebra, whether it's FOIL, the distributive property, combining like terms, they apply in the same way. There's a few intricacies that go along with the complex numbers, and I'll explain those by example when we encounter them. The first example that I would like to tackle is to expand and simplify the complex number 2 plus 3i times the complex number 4 minus 5i. Now notice, in this complex number, the real part, the imaginary part. The coefficient on the imaginary is 3, so b is 3. Real part, the imaginary part is negative 5i. The b is negative 5. Now, we're going to FOIL this just like always. So to start out, I'm going to say 2 times 4. That's going to give me 8. And then I'm going to go ahead and distribute a second time. 2 times negative 5i, which is negative 10i. Extinguish my first term. Now I'm going to move to the 3i. 3i times 4i is plus 12i. And positive 3i times negative 5i is minus 15i squared. We're going to combine some like terms. So we end up with 8. Negative 10i plus 12i is plus 2i. Notice that I combine those just like I would as if it was an x. If I had negative 10x plus 12x, you know, they're like terms. They have the same variable to the same power or the same degree. And then I have minus 15 times, now this is the cool part. This is going to drop out. This I squared, we know that I squared as defined earlier is really just the number negative 1. So what we're really looking at is negative 15 times negative 1, which is 8 plus 15, which is going to be 23. And we take along the 2i. So this is our complex number. The real part is 23. The imaginary part is 2i. A second example that we're going to take a look at here, called example 2, we're going to rationalize the denominator of this complex number. And it doesn't really look like a complex number in the very beginning because the example that I want to take a look at is 13 over 2i. Now this 13 over 2i, there's several approaches to something like this. You know, some students may say this. They may say, well, you know, 13 over 2i, that's really 0 plus 2i. That's the complex number because the real component is just 0. And following the procedure that we did before, they would say, well, it's 0 minus 2i over 0 minus 2i. And they're 100% right. This would work. This would work. But it's going to cause you a little bit more work in the long run. It doesn't have to be that complex. So that's not going to be the approach that we decide to take. Instead, what we are going to do is we are going to multiply the top and bottom by I. We know that if we get I squared, it goes away, at least in the denominator. So that's what we're going to do. We're going to say, well, if I multiply the top and bottom by I, then an equivalent form would be 13i over 2i squared. And knowing that I squared is really just the negative 1, we'd end up with 13i over negative 2. Now, most of us say we don't want to leave the negative in the denominator, so we'll finally rewrite this thing as negative 13i over 2, final answer. Now, how do we use all of this with the quadratic formula? Because that's really where we're going with it. That's our first true application. We know that the quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now yesterday, or several days ago, we had talked about something called the discriminant. And the discriminant is the number that is underneath the radical sign. We call it the radicand. And what is that number? If it's positive, we found out that there are two real solutions. They could be rational or irrational. And if the discriminant was 0, there would be one real solution, and it would have to be rational. And we said that if that number underneath there is negative, that there will be no real solutions. And I told you and alluded to the fact that they would actually turn out to be two imaginary solutions. And that is what we're going to investigate right now. Now I want you to recall the pictures that I drew yesterday. If we have no real solutions, that means that wherever our parabola is drawn, it will not cut through the x-axis. If I have real solutions, such as this one here, those solutions are the x-intercepts when y is equal to 0. Now, let's look at an example. Let's take the quadratic equation 3x squared minus 2x plus 4 is equal to 0. Let's take this equation and we're going to use the quadratic formula above it. So, knowing what we have x is equal to, well, remember, a is 3, b is negative 2, and c is positive 4. So negative b is 2, plus or minus the square root of b squared, well, negative 2 squared is 4, minus 4 times a times c, all over 2 times a. Now, I would expect any student at a minimum to write this out. At least this part here. Now we're going to simplify. Do not just dive in your calculator because it's not going to help you. A lot of times that's where the mistakes happen. What I tend to do is I say, well, I'm going to simplify my radical on my second pass. 4 times 3 is 12. 12 times 4 is 48. 4 minus 48 is negative 44. Aha! The discriminant is negative 44. At this point I know I have two imaginary solutions. Denominator reduces to 6. Now, just as we did before with these imaginary numbers, what we're going to do is I'm going to say 2 plus or minus. And I'm going to break this into I, in terms of I. Now, negative 44 is really root 4 times root 11, and then root negative 1, but we know that that's I. So this would be a simplified version of it, over 6. Now let's write it out one more time. 2 plus or minus 2 root 11 I over 6. Now, some people are going to say, oh, I can simplify 2 and 6. No, that's not true. The top has to be in a factored form. And here we're in luck because there is a GCF in the numerator. The GCF, or greatest common factor, is 2. So x is equal to, if I factor that out, I'm left with 1 plus or minus the square root of 11 I all over 6. Now, this 6 and the 2, those will simplify. And when it simplifies, we have x is equal to 1 plus or minus square root 11 I over 6. These are the two solutions. Now, if I asked you what the real part of the positive solution is, so let's just look at the positive one, you would say that the real part is 1/6, because I could expand these fractions as 1/6 plus or minus root 11I over 6, equivalent fractions. And so the real part would be 1/6, and the imaginary part would be root 11I over 6. Okay, class, I tried to put a little bit of that video together to help you with section 1-5, which is the complex number, introducing the imaginary unit, and we had to throw in some stuff with the quadratic equation. I know we're crunched for time. I hope that some of those ideas help you in some of those examples I went through. By no means have I hit every aspect or said everything. It was just something I put together that I'm hoping helps. There's a lot of resources out there. You need to read the chapter. You definitely do. There are intricacies that need to be explained that may be explained in a different way. So don't hesitate to come in and ask me questions if you have those before school. It's down at crunch time. We're moving on. So I need you to be fluent and understand the complex number.